Okay, so today we will continue our lecture regarding one more example about Annulus, and after that we're gonna move to the next chapter about equation of change, or equation of motion and equation of continuity. Okay, let me open the slide. Okay, so basically we've done the 1.2, the Newton's law, and after that about the convective momentum flux, and then last week we learned about the shell momentum balance and also falling film, and then the 1.6 is about the flow on the circular tube, and then one more is about Annulus. Okay, and after that, so I'm gonna open the 1.7 about the momentum balance of Annulus, and after that the momentum balance for equation of change, and then we will continue on Friday on momentum balance derivative. Okay, let me open this one. Right, so over here. Okay, so now let's consider another problems about the viscous problem. So so previous one we talk about the flow in cylinder, okay, where the fluid goes downwards. Okay, and then you also have assignments about you have the pipe, but you have a falling film inside cylindrical wall, yeah. Okay, so it is open system, and then you know the boundary condition as well. Okay, now for today, let's consider another viscous problem in cylindrical coordinates. Okay, and it is a steady axial flow of incompressible liquid in annular region. So annular is actually there are two coaxial cylinder with a different radius. Okay, so this is called annulus. Okay, so in annulus you have outer pipe like this. Okay, so this pipe has a radius of capital R. So from here they have a capital R, and then they have inner cylinder as well. Okay, and they are coaxial. Coaxial means they have similar axial. Okay, so they have a similar center. Okay, so it's called coaxial. And then between these two cylinders there is fluid flowing, and in this case is the fluid flowing is upwards. Okay, this may be very famous example of this annulus is about, for example, in heat exchanger, in double pipe heat exchanger. Okay, so first we have to think about the phenomena. Okay, what we know that the velocity on the wall, just inside the wall, that should be always 0. Okay, so first what should we do? First we have to determine the coordinate first. the coordinate usually would be the origin of the flow, okay, because the flow is from down there to the upwards, yeah, because this is the upwards here, see, yeah, it is the upward, so that means the flow from down to up there, so the origin would be at the bottom, okay. In previous case, if it is start from just flowing and then just falling because of the gravity, we can start it from the from the top, because it is the origin of the motion. Okay, so then this is the coordinate, yeah, so this one is r, and of course the with the axial is called z, right? Okay, and then the first one, and then the second one, after we determine the coordinate, we can identify non-vanishing component. Okay, remember, I always write the steps down, because in the exam they will always ask the every steps would be asked, okay, and then if you're missing one steps, then it's it's not would be you have to pass all of the points, right? So be careful if you do try things but you didn't determine the coordinate, for example, or you draw different coordinate, that it would be wrong as well. Okay, so first one, what can we postulate? Okay, what can we postulate? Right, okay, so I think I should close this one, yeah. So we know that we have phi to the z, yeah. So this is actually the fluid, yeah. The fluid is on the between the two cylinder. Okay, so first in the previous case, we know that we have phi z, and the phi z is a function of r, okay, and then we don't have phi r, phi to the r, that way we don't have that one. We don't have phi theta, and then because it is inside the cylindrical wall, and it is a closed system, so it is so we have the pressure difference, and the pressure difference is function of c. Okay, so here the non-vanishing component would be tau rz, or tau zr is the same. It's actually mu dv over dr. Why you find the non-vanishing component is this one? Because now we know that phi z is actually we have phi z, and it's a function of r. Okay, now up to here, any questions, please? Is it quite clear? Okay, right. It is quite similar with the previous one, but I think the difference would be about the boundary condition. Yeah. Okay. Okay. So we can also make the momentum balance over the cylindrical shell of liquid, and if we think about it, the shell that we make would be somewhere thin line around here. So it would be also a very, very thin line. Yeah, a very, very thin line of shell. Okay, and then that also the delta r. Okay. Okay, and then because we make the similar the momentum balance like previously, like in the cylindrical falling in the cylindrical tube, is also the same. So then we can just go forward with that, and then find the d over dr of r tau v tau rz equal to this one, and then would be become to this the capital P minus capital L. Okay, compared to the previous problem, the capital R is actually we put it actually positive, that one. because in the positive, because the sign of positive is because the coordinate z is in the direction of opposed to gravity. Okay, in the previous one, if you look at the problems, the p should be minus rho gz. Okay, and after that, we integrate this one, yeah, the d over dr of r tau rz. Okay, and this will result to the similar, we call this the momentum flux profile, yeah. Okay, for this case, we have to really think careful about the boundary condition. Okay, because we have to think again the boundary condition that's related to this phenomena. Okay, so we have to think what is the boundary condition related to this phenomena. Okay, now we can't determine the C1 like in the cylindrical wall last week. Okay, in the cylindrical wall from last week, if you remember, if this is the cylindrical wall, we know that at r equal to 0, the tau rz is finite, yeah, for that case. Okay, but in here we know there should be something finite, but we actually don't know where. Okay, so because we can't determine the C1 immediately, but because we don't know the momentum flux at r equal to kr and also r equal to r. Okay, remember, because this is the equation about momentum flux, so the boundary condition should be related on the momentum flux. Okay, so we have to find the momentum flux at r equal to kappa r. So they write the inner wall, the length of inner wall is like a factor or a fraction, and the fraction is called kappa. Okay, and the larger one at equal to r. Okay, so at inner cylinder, you know, in the wall on the cylinder, or the just inner before the r, we don't know the momentum. We know there is a momentum, but we don't know that one. Okay, but however, we know that in r equal to is it, oh no, it's not k. Okay, at lambda r is somewhere along the wall, sorry, somewhere along the fluids here, there should be a maximum velocity. Okay, because this is velocity is zero, but somewhere here should be a maximum velocity. If the velocity is maximum, so the momentum flux would be equal to 0. So somewhere here there would be flux momentum equal to 0. So let's say at lambda r there's maximum velocity, so the momentum flux is 0. Okay, so now we know the boundary condition. The first one would be at r equal to lambda r, so tau rz equal to 0. We don't know where is lambda r, but it should be somewhere along the fluids over here. Okay, so after that, so that we can put this tau rz equal to 0 at r equal to lambda r, and we will obtain this one. Okay, 0 equal to this one, and then lambda r plus c1 plus lambda r, and then we can get c1, right? And after that, when we solve the equation for c1 and substitute to this equation, we will get this you know, the equation. Okay, how to do that? It's not explained in the book, but you can try it by yourself, and then you can have some there should be some equation. But what happen if I have a different equations? As long as you do the rightly when you substitute and mathematically, that is fine. Okay, so we doesn't consider the right one for the, so if you have different equation, that's fine, because we're not interested in the mathematics of that, but usually we want to know what is the equation and also what is the boundary condition. Okay, and so you can make the profile. If you can make it like this and then make the profile, that's also good. Okay, now that is the momentum flux profile. Now, how to get the velocity profile? Anyone? How to get the velocity profile of inside the wall?
To substitute the shear stress.
We should substitute the tau RZ to the Newton's law, right? Okay, so let me write from beginning again here. So usually this is to identify the non-vanishing component, and the number T is develop shell momentum balance. Usually the number 3 would be sketch shell momentum, or maybe thin shell, yeah, thin shell, and write the the direction. Okay, and after that is number 4, develop the momentum balance, and then you have, and then after that you get this one, and number 5 is this is number 5, integrate the shell momentum equation, and then number 6 is find boundary condition. Okay, and then this one is usually number 7, write the momentum flux equation. Okay, and number 8 is only find velocity distribution by substitute tau RZ to mu minus mu dvz over dr. Okay, so at least by trying to do it by yourself, you know the steps, yeah? So when you do it, it's really good to put that one. Okay, so this is when we substitute the equation that becomes this one. And then to integrate again number 9, yeah? The number 9, we need the boundary condition. Boundary condition should be related to the velocity. Okay, and we know that at the wall the velocity would be equal to 0. So when r equal to kappa r, the Vz equal to 0, and r equal to r, the Vz also equal to 0. Okay, so then there you have it. Here we substitute the boundary condition, this one, to here. Okay, and then the first one is 0 equal to that one. So this is the simplified of that one. So but you I really suggest you try it by yourself. Just try to do it. If you substitute to here, so what happens there, and then from the integration we found the constant. This is the C1, and then you can also get the C2, and we also get the correlation between kappa and also the lambda. And after that, then we get the momentum flux distribution and also the velocity distribution, this one. Okay, I really strongly suggest for you to try by yourself to do it, that one, because usually the constraint in the exam is the time is actually quite limited. For example, 2 hours for 2 problems. So it's basically to obtain this one up to the momentum and momentum flux distribution and velocity distribution is around maybe around 50 minutes. So at least by doing make a practice by yourself, you can actually calculate is can you do fast enough, yeah? Can you understand enough to do it maybe with a good path, so you can do it in about 50 minutes per problems. Okay. Right, so again, so in the implication, we can calculate the V maximum with delta R, and we know also calculate the average velocity, and also the mass flow and the force. This is called the force on the, even in the, in the inner and also the outer. So this is the additional one, yeah? So inner for the force is actually, we can call it also drag force. Okay, the force that needed on the solid surface by adding the multiplying again the tau at r equal to kr, which is on the inner wall, the smaller diameter, and also on the larger diameter, and then we add them up. All right, so that is about the annulus. Anyone would like to have any questions? And for the assignments, don't forget to put it submit, yeah, if you have do this submission, so I can have a look your about your work. All right, anyone have any questions? All right, okay, so if not, then I will open the second one. So the second one about the equation of change. You can open it also in your in your laptop or something, so you can try to check it as well. Okay, so this one in the book, it is in chapter 3, yeah, so it is a different chapter with the previous one. In chapter 2, if you look at there, it is there we have example like a falling film, and then the flow inside the cylindrical tube, and also another one is I think the annulus. Okay, and then there's some also several examples that it is not mentioned in here, but if you want, if you can have a look. For example, flow between two liquids, or flow around sphere, yeah, but the spherical coordinate is not included in the exam, so it is for just additional knowledge if you want. Okay, so now I would like to start the third chapter is about equation of change for isothermal system. So we consider the system is isothermal, the temperature is the same, that means the properties also doesn't change as well. So even the rho, the density, the the viscosity is also, we can consider is constant. Okay, so so this is the background. I'll write it from the book as well. So shell balance, it can be used for to develop a novice problem, just simple problems. Okay, like the flowing fluid, or just with one direction only, direction with the velocity to the z. Okay, or maybe the velocity to the just to that z, yeah, that one there. Okay, and then with the with the shell balance, it also, we need some more time to set up the shell balance for each problem. Okay, so remember how it is, there are several steps, yeah, in my case up to 8 to 9 steps, right? So from identifying the coordinate, and then identifying the non-vanishing velocity, and after that you have to make the thin shell, and then check the direction and so on, and after that you make the shell mass balance, shell momentum balance, and after that you get the differential equation of the momentum flux, and then you can integrate that one and then find the boundary condition related to the momentum flux, and after that you have to put the Newton's law of viscosity into the momentum flux, and then you get the velocity differential equation, and after that you can do the integration again with boundary condition, then you get the velocity profile, right? So it takes me some years to remember all of that one, yeah. So it is quite tedious and also a lot of steps, okay. So, and then also there are some problems that is non-linear motion. For example, what happens if the motion is like a function of theta, okay? It is an angular motion, okay? What happened that one? What happened if we have a combination between let's say the R, but and also a combination with the or the combination with the R, for example? What happened? The shell balance can't do that. Okay, so in order to solve the more complex problems, or more non-linear problems, we will learn two equations. Okay, the first one is called the equation for continuity, or the mass balance, and the second one is the equation of momentum, or the equation of motion, which is actually the momentum balance. So that this is actually the template, yeah, we can call it that is a template, the template for the equation, that it is we can see it on the book in the appendix B, and then we can check the equation and then check what is the non-vanishing non-vanishing components with that one. Okay, and this equation will help studying all problems in isothermal flow of fluid. Okay, so before we see what is equation continuity, I would like, of course, to give you some understanding how that equation of continuity is developed. Okay, so equation of continuity is actually based on the mass balance. Okay, in the mass balance, so let's consider in a Cartesian diagram, we consider this fixed volume element of this one. Yeah, this is the fixed element of the volume element, and it has a length of delta x, and also like a cube here, delta y, and also the height of delta z. Okay, yeah. So and after that okay, so can you try imagine that? Yeah. So just consider we have a piece of a fixed volume element, delta x, delta y, and delta z. Okay, so this can be actually the volume. Okay, right. So we know that in mass balance that the mass in minus mass out would be equal to the accumulation of mass, right? And then let's talk about not only the mass but actually the rate. Okay, so rate is actually mass divided by the time. Okay, so we talk about a time over here. Okay, so so that means the rate of increasing the mass, okay, that would be the volume of the volume of this one, okay, multiply with the change of density over time. Okay, do you remember that a volume volume multiply with rho equal to the mass. Okay, so if it is if the density is changed with time, so also the mass also will change with time. Okay, so let's write this one. So the volume divided by the change of density over time, we call it dou rho over dou t. Do you remember in calculus why we call it dou? Anyone? It is a partial derivation, yeah, because actually density, it can be function of distance, it can be function of x, can function of y, or function of z, I don't know, yeah, it can be maybe it's not uniform, tidak seragam, and also function of temperature. So if it is a partial derivation, it is only function derived with respect to time. Okay, so this is the rate of increase. Now, so we have to consider the rate of mass in. Okay, so the rate of mass in is actually the one that, so we have to consider the one that so let's say that there are a v to the x, that one there's a stream that coming inside the x, and then this is also from outside, and also there a stream coming from you know, a positive z and positive out, and also the one that going to the y and also the y out. Okay, think about it. You have a block. What do I have? Oh, I don't have the block. Let me check. Okay, I just have the T. Yeah, sorry. Okay, I just have the T. Let's make this as the box. Okay, so you consider there is the x, yeah, the x over that one, the one that goes into the x over that one, and also y from behind this one to that one, and also z from down there to the up there. Okay, so let's say this is the block. Okay, now to consider what is the rate of mass in to the x-axis, like that, or the x-axis like that, then would be is actually equal to rho, yeah, rho v x. Okay, so let me write it in here. So it is actually rho multiply with vx at x equal to x. Okay, and then this velocity, then it should be multiplied with the cross-sectional area, and the cross-sectional area for this case is the delta y multiplied with delta z. Okay, and then minus the outer one, which is the outer one is this one, yeah, in in my case is this one, is the inlet, and this is the outlet. So again, the velocity of x at x plus delta x. Okay, so rho multiplied with vx at x plus delta x, multiply with again with the cross section of the area over here, which is delta y multiplied with delta z. Okay, so this one, and then we can just group them together into this part. Okay, so delta y delta z of the rho vx at x minus rho vx at x plus delta x. Okay, and after that you can consider around for the y, which is from here into that one. Okay, and then you can, that will result into this one, but the cross-sectional area now become delta x multiply with delta z. So you have to think about the cross-sectional area as well. Okay, and after that you find the vz, yeah, that one, from down there to that one, and the cross-sectional area that you're looking at is the delta x multiplied with delta y. Okay, and this one. Okay, and after that, let's divide all of them, divide both sides with delta x, delta y, and delta z. Okay, so divide both sides with delta x, delta y, and delta z, and also make this one the delta x, make it limit, so really small. Delta y also really small, and then delta z also really small. So then it is become the limit. So in the this one, in the sides, if we divide with delta x, delta y, delta z, this will be eliminated. We can eliminate this one. So in this part is the dou rho over dou t, the partial derivation of rho to the t. And then this one is this is minus, because the limit should be always x plus delta x minus the x, right? So this become negative, and then so this one is the derivation with respect to x, this is derivation with respect to y, and this is derivation of respect to z. Okay, so there you go. And then this is the basics of equation of continuity. Okay, so that is the general writing, or the general equation for equation of continuity, which is based from the mass balance. That means if you have an increasing mass, or increasing or changing in density, then it would be equal to this one. So what happens if the density is not changing? What happens if the density is constant? We know the value of density, but the density is constant. So if the density of constant, then this one equal to 0. Yeah, okay. Okay, so this is called the equation of continuity, which is describe the time rate change of the fluid density at the fixed point of space. Okay, so this is the rate of the increase of mass volume, and this would be the divergence of rho v. If you look at here, the v is bold. That means would be equal to v, yeah, or vector. Okay, so this is a vector, the velocity, and rho is a scalar. Okay, and this one is the divergent to the vector here with any in any function. So if the v is function, so the divergent means that if v is function of v is a function of x, y, and z, so the derivation should be with respect to x, respect to y, and also respect to z. Okay, so this is actually the net rate of mass addition per unit volume by convection. All right, so that is first one is the equation of continuity. The second one, so let me continue to explain about this equation, and then on Thursday we can go to the examples. So we can focus on discussing about the examples. Okay, now the second one is the equation of motion. The equation motion, persamaan gerak, it is based on the momentum balance that we built it on the second chapter. Okay, so again, we still consider a fixed volume like this with delta x, delta y, and also the delta z. Okay, and then if you remember, in the equation of motion, we also have the arrows, yeah, there. So you can consider the cxx at x, cxx at x plus delta x, right? And then psi xz at z, and then psi xz at z plus delta z. And also if you consider the y, psi y x at y, and then psi y x at y plus delta y. So you can try to do that. If you're very curious, you can try to derive it by yourself, yeah, there. And so it is written that the increased momentum, if we have the addition of momentum, would be equal to the rate of momentum in minus the rate of momentum out, and then plus the external force on the fluid. So the external force on the fluid, it can be gravity, it can be usually both gravitational forces. Okay, so here with the similar one, this would be equal to the rate momentum in with respect to xx, yeah, this one, and then with respect to xy, and also respect to yz, again multiply with the area. Okay, so we multiply with the area, and there is an external forces, and for example for the x component, it is rho at g when in the x direction, and then multiply with the fixed volume element, which is the x, delta y, and delta z. Okay, so in summary, when you derive it and then you try to do it, then for the x coordinate, for the x-axis, you will end up with this one, dou over dou t of rho vx equal to this one, yeah, with its rho gx. But however, we also consider the with respect to the direction of y. If the motion with respect to y, we can get this one. Or if we with respect to z, we can also get this equation. Okay, so just think about it, that there are three possibility of momentum from to the x-axis, to the y-axis, and also to the z-axis. So it's actually there are three equation of motion. Okay, this is looks like so many, but in reality later on when you do the practice, there would be a lot of them is actually equal to 0 if it is not applicable, right? So then later on you can just eliminate that one. Okay, so here there is a rate of increased momentum, addition and minus the molecular transport plus g external force. So this is the the general area to read this one. Again, if you forgot or if you just I don't understand about this one, you can go back to the calculus, yeah, where what is the definition of dou over dou t, what is the definition of divergence, okay, what is the definition of vector. So please check again your understanding regarding that one, yeah. That's why we need the calculus 1 or 2 in the first year, and then also the mathematical analysis in the second year, because we're going to actually use it in this transfer phenomena, okay, in the third year. Okay, and then this one, this would be later on about the mechanical energy. Later on about the second one, this is the dot product velocity with the equation of motion. This one with both the velocity, yeah, related to the velocity, that one. Okay, and if the equation is related with the angular motion, it is called the cross product between position of vector. This is the equation for angular momentum. For example, if we consider fluids that is actually in angular, for example in a cyclone, or in like in the centrifugal force, something like that, we consider about the angular momentum, then we can use this equation. Okay, so this one, for example, yeah, that so this is an example. Okay, so now because it is maybe some of you are confused why we are so many equation. So what I need to do, what you need to do is, now you can open the appendix B, you can open the appendix B in here. Okay, so let's open the book, yeah, and then you can open the appendix B, which is fluxes and equation of change. Okay, in this appendix B, they actually they have listed all the equations that you needed. The first one is the Newton's law of viscosity. So, okay, I don't know what is the Newton law for tau or z, for example. So you can find it, okay? So how to read this? So in each subchapter, for example, B1, Newton's law of viscosity, we have the or the general writing for the equation, and after that you can see that it is in Cartesian coordinates, which is a function of x, y, and z, or a cylindrical coordinates, or which is function of r, tau, theta, and z, or in the spherical coordinates, right? And then the second one, the number B2 is for later on for the Fourier's law of heat of conduction. So we're gonna just skip it, but you can see it here. Also, there is a Cartesian, cylindrical, and spherical. And then the third one is and the third one is called the fixed law. The fixed law is for mass transport. Yeah. So that's why in transfer phenomena it is like a module. So once you understand about the momentum, you can govern the equation. Would be easier for you to learn the heat transport and also the mass transport. This actually is a similar approach. Okay, so now let's open the B4. Okay, usually in the class before the pandemic, I would ask the students to have a copy of this one and always bring it to the class. So when when you have the exam, you can have this piece of the appendix and just have a look and then just rewrite the equation. Okay. So here is the equation of continuity. This is for the Cartesian coordinate. Yeah, this one is the one that we developed just before, and then this one is cylindrical coordinates. That it becomes, there is a function of Vr, Phi theta, and Phi z. The way they derive it is similar with the Cartesian coordinates, of course, but with different type of shell, and then those shell is also approach zero. If you really curious about that one, you can have look on the chapter 1, I think, about how to develop this one, and also for spherical coordinate if you want. Okay. And then in appendix B5 is the equation of motion, and there are two types of equation of motion. Okay, the first one is the equation of motion is in the term of a momentum flux theta at the tau. Okay, so in the in the left side here, in my left side, this is about the velocity, but on the right side, again there is a pressure difference, there is a tau or the shear momentum or the momentum flux, and also there is a gravity. Okay, seems familiar, right? Because we also understand in the shell momentum balance, we learn there is a pressure contribution, and there is a tau or momentum flux contribution, and also there is G contribution, and they will also write it here. Okay, and this is the cylindrical coordinate, and also this is spherical coordinate. Okay, however, there are also the second equation of motion, but in terms of velocity, and it is in the B6. So in the B6 here, the equation motion for Newton fluid in the B6 over here, but it is actually both sides is a function of velocity. This case is really great if you only have boundary condition related to the velocity. For example, you don't know the boundary condition regarding the momentum flux, so only get the boundary condition regarding the velocity, and you can apply into this one and then you can try it, yeah, just to, because this is a function of x, yeah, and then this one. So we will go through the examples on Friday, but you may want to see, for example, in a steady state, do we have dou Vx over dt? So in steady state we don't have, so we can eliminate that one. For example, it's only there is a few phi to this z, yeah. This also can, so phi x equal to 0, phi y equal to 0. This also can be cancelled out. Okay, and even in the second derivation also it can be cancelled out. So later on you will do a lot eliminating, you know, this equation, so we can get more simple equation. Okay, I think personally I do like this equation of motion because it is easier for me to derive that one rather than to sketch from the beginning about the shells and so on. But of course in this transfer phenomena we will ask you, so the one problem would be about momentum balance and the second problem would be about momentum motion. All right, so I think that's all for today. So let's have a discussion again on Friday, still online, because the condition for the COVID-19 looks quite increasing. So keep safe and keep healthy. So I really just wait for another information when we can go inside the campus for this class. But let me, if you think that you really need this session after this, yeah, because, or maybe just before the for the tutorial or before the exam, let's do that on campus. Okay, so but at least let me deliver the materials to you, and then it is recorded and you can recheck and then redo that, and then after that if it is possible we can go to the campus. Okay, and I also hear that Helena also now in traveling to Indonesia, so I hope she can also get here, yeah. So that would be good. So I think that's all from me. It's almost 9 o'clock, and then thank you for attention, and then I'll see you again on Friday. All right, thank you everyone. Bye bye.